Okay, so I think the first thing we'll do here is all right, I just kind of cover some uh, administrative type things. I have updated the course schedule that is on Moodle, and um, so that also includes both this uh, canceled class and uh, just basically being one lecture behind on top of that. So um, we do have the exam on this Friday, and we'll cover some new material today. And I will determine afterwards, after today's lecture, on how much we will include from this lecture in the exam. So let's see what else to share. Um, Let me just go ahead and share my entire screen. Okay, so I've uploaded a preview of the exam, and so I've listed a bunch of topics here. I We can talk about this briefly, but for this exam, we really haven't gotten very deep into doing problems and that type of thing. You've done some pretty simple MATLAB exercises and stuff, but really haven't gotten deep into a lot of math. So what I'll be doing is kind of emphasizing concepts, right? So understanding the concepts of things. So you can go down through this, and I hope this is helpful. Emphasize the PowerPoint presentations. Okay, so I think that will uh, benefit you the most when you do that. I can also, for those of you that have not had me before, so typically this is last year's exam, and I've updated the date, but I haven't done anything more than that to create this year's exam. It's going to be a little bit different because last year I did not cover any analog modulation, and we got a little bit further. I gave the test a little bit later in February. Decided to move it up earlier this year because what happened last year is that they had the exam one, and then boom, almost right away they were having the midterms. So trying to space it out a little bit more. So there's a lot of equations on here that we haven't covered yet, but some that we have, like the uniform distribution here, and the Gaussian distribution, and that type of thing, right? So when I give exams, I'm normally not concerned about you knowing a particular equation by memory, because in practice we look up equations, right? We use them enough times and we memorize them, but we don't purposely go out and memorize equations. But you do need to know how to use them, right? So you might be given equations like this, and you need to recognize that this is Shannon's capacity theorem, and that the capacity gives you results in bits per second in terms of capacity, and that this is the bandwidth, and this is the signal power and the noise power, right? And to be able to recognize that if you want to increase the bandwidth, the capacity overall, right? That's our kind of our job as communication engineers. If we want to increase the capacity or data rate, then we can either or all increase the bandwidth, increase the signal power, or decrease the noise power somehow, right? So we can do any of those type of things, right? So you would need to be able to recognize that equation for what it is and to apply it in a particular situation, right? So then I have things like which this question actually gave me a lot of trouble last year. But what block of the communication system in figure 1 here is responsible for adapting the information to the available communication medium, right? So you would recognize that the channel is really the communication medium, and that it's the digital modulation stage that is responsible for adapting the information to that channel, right? So that was the correct answer. In the presentation, when first or second week, that this diagram shows up, and I think on 3 different slides, and I describe each of these. On the first slide, I described the channel on its second slide, and then I described the receivers on the third slide. Like name the 3 features of a signal, also known as a carrier, that can be modulated to carry information. Well, that could be the amplitude of the wave, the frequency of the wave, or the phase of the wave, right? So, we can get even more sophisticated and super geeky, researchy type stuff, but those are the basic 3 that you're using to encode information onto a signal to be able to communicate it, right? Randomness. Describe 3 examples of randomness in a communication system, including the source of the randomness, right? So we talked about that a little bit. There's ultimately thermal noise, and that we model as white additive Gaussian noise. And we also might have some phase in terms of if you have a mobility between the transmitter and the receiver, then the phase of the signal is going to change, and all. So there's a few others. So here's the phase of a signal in a particular system can be described as uniform random variable with support from pi over 2 to 3 pi over 2. Well, you could write that as minus pi to pi or 0 to 2 pi. I chose to do it from pi over 2 to 3 pi over 2 just to make the question interesting. And then I asked to find the mean. Now, we actually derived the mean using starting from this equation, and we did that in the lecture. And I think when I didn't have that formula on here, and I think I gave it during class, and they wrote it on the board and stuff. So, all right. So hopefully that gives you some ideas of how the test will be. If you prepare for it, it should be easy. Not always easy. It just depends on how you prepare for it. But I'm trying to give you a little bit of flavor for how I do exams. I may add some based upon today's lecture, also depending upon how far we get and all that. So I did grade assignment 1. That's out there for you, and I have also added a homework assignment that for now focus on your exam. If need be, we can postpone this, but you do. So I created this today. Again, using MATLAB, you're going to play around with some uniform distributions and some Gaussian distributions. So I can give you some examples here real quick on how that's done. So MATLAB has a uniform random generator that you can plug in your limits on, and you can also provide it a size. By default, you when you provide the size, MATLAB gives you a matrix, even though they say they give you a vector here. It if you just put in a 10,000 here or 1,000, it's going to give you 1,000 by 1,000. So what you can do is create an array that let's see, do I have that somewhere here? I was going to log in here real quick. So then also there is a rand function, but note that it gives values in the interval of 0 to 1, which yeah, you can scale things to adapt that to other intervals, but they also provide this function to give it to you directly. I ask you to do a histogram, and yeah, just calling the histogram there is fine. And then I also ask for Gaussian or normal distributions, and note that this will give you a mean of 0 and a variance of 1, I think. So I don't ask you to actually calculate the I don't actually ask you to calculate the mean and the variance after you've created it, but it'd be a good idea for you to do that just to check. So I can run through some examples here so we can say that n is equal to 1001 as a dimension, and then I can say let's say minus pi comma pi n, and we see that it generates a vector 1,000 by 1 in dimensions. And now I can simply plot that as a histogram. And you see it looks pretty good. If we did a lot more samples, then we should converge a little bit more to a what we would expect as a uniform random distribution. You can calculate the mean of that. You can calculate the variance of that, right? So our variance is kind of high. Well, that's okay, because this is a uniform. I'm sorry. So then we can also say that let's see, what is that? That's a rand n, right? Yeah. And then we can create this, and now if we look at the mean of G, that's pretty close to 0. If we look at the variance of G, that's pretty close to 1. Histogram, we'll look at that real quick. Now that looks like a nice bell-shaped curve, right? So then I also ask you to, where did it go? There it is. So I also ask you to do it with a mean of 10 and a variance of 5. And so the way to do that mean of 10 and variance of 5. So we can just scale the results. So we can say that, let's see, G times. Now, let's think about this. The variance shows up in the Gaussian formula is a square term. So you will find, with a little bit of playing around here, that you're best off. It's a mean of 10 and a variance of 5. So we're going to multiply this by the square root of the variance, and then just shift everything to account for the mean, right? So now if we look at, let's see how good I did. Okay, so now we've got a mean of 10, and let's look at our variance. That's awfully close to 5, and so we'll finally plot that. And so we see here that even just with the default axes here, it's showing up as a about a mean of 10. And you can look at this, and yeah, it looks wider than just a variance of 1 gave earlier. So so that's it. That's pretty straightforward. Again, for now, you can worry about the exam. I think I made this due like Thursday of next week, so I think that should give you time to study for your exam and also get the assignment done, especially since I just showed you how to do that assignment. So a couple of notes on the assignments. Then so I did grade, and I just gave you a little bit of feedback on each for each one. And so please follow directions, right? I said you didn't have to worry about all those GitHub directions, but I did ask for both a figure and a PNG. And you know, I want both of those. A lot of people just gave me one or the other. Also want the .m file, and I prefer that if you're not putting it in GitHub. I'd like that .m file as a file in the submission, right? Not pasted into a Word doc or a PDF. Some of y'all did that. That's, I get it. You're trying to kind of write a mini lab report or whatever, but I want to be able to run your file in MATLAB just in case you didn't get everything exactly right. I want to run it and show, give you some feedback on what you did wrong or how you might improve your code and that type of thing. So include that separately. You can use, I think the command is save fig, and that will save your current figure. You can also do it from the toolbar of the figure itself, and but by default you'll save that as a .fig, but you can specify the extension, at least in the command save fig, and save that as a PNG. I noticed some of y'all may have done some screen grabs or used some tool or something like that. You can do that right in MATLAB and include that in your script. So I think it's savefig. If it's not, you should be able to do a search on MATLAB savefigure, and it should pop right up on how to do that. Having a PNG is nice because then I can just click on it and look at it, right? Having a fig is nice because now I can open that up in MATLAB and I can zoom in on it and I can look around on your plot. So all right, so Also, yeah, I'm, trying to give you an idea on how to do things in lecture, in class, like I just did for the random noise, but make sure you read through it and do it right. A few of y'all ended up with like 100 kilohertz instead of 100 megahertz, and maybe you're confusing the first and second assignment or something like that. But make sure you do it completely, label all your axes, put a title on your plot, all these things, right? So, all right, that's good for that. Let's get back and we'll try to get on with the lecture now. Any questions up till now? Okay, so we briefly kind of introduced some of this last week, last Friday, but just as a preview, right? So we'll go through this a little bit more deliberately now. So the first thing we want to cover is the state space representation of our signals. And so when we've looked at these signals, they've been cosines or exponentials, that type of thing, right? And that's nice, right? So you worked with those in MATLAB, and you see this big long carrier and mathematical representation. A vector representation is going to give us a more intuitive or graphical way, in some ways, of representing our signals. So let's step back first and kind of recall what vectors really are, right? Maybe by the time you're a senior, you've been working with vectors a lot now, and sometimes you don't even kind of remember or think about where they came from in terms of their basis, right? So vectors are described by orthonormal basis functions, right? So they're orthogonal and they're also normalized to 1 for these basis functions comprising n dimensions, right? So, in general math, we might have a dimension x and y. That's 2 dimensions. Maybe we've got 3 dimensions and we add in z, so x, y, and z. So we might have unit vectors u sub x, u sub y, u sub z, right? And then we would have a vector that would go from the origin to some coordinate, right? That's specified by coefficients of those basis functions, right? So, or the unit vectors. So where each unit vector is orthogonal to the others, right? The x is orthogonal to the y to the z, right? And the unit vectors themselves are by definition normalized to a length of 1. Therefore, when we put a coefficient up front of it, it can describe the length along that axis, right? So these coefficients are the projections of the vector onto those unit vectors. Now think about, before I show you the next screen, what operation do we use to determine this projection, right? I'll give you a minute to think. And so here's what we mean by that projection, right? So if G is our vector, then it projects along the x-axis. Maybe there's a y-axis up here also, but right now we're projecting its length on the x-axis, right? And so, oops, wrong direction. So we use the inner, or most of the time we call it the dot product, right, as engineers. And that can be noted in a few different ways, right? So this is maybe the notation we're used to, where we have a vector 1 and a vector 2, and there's the dot product, right? So this vector 2 could be the unit vector, right? Which would give us then the projection onto that, right? And we can do it in terms of the cosine of this angle here, and then multiplying the two vectors, that also gives us a dot product, or we can calculate it in this way, right? So if we have two arbitrary vectors, then yeah, this equation handles this. If we're looking at the unit vector, then maybe this V2 here would be a 1 in the x direction, and then 0, 0 in the y and z directions, right? So that would be its representation. So, so a vector here then is a linear combination of orthogonal unit vectors with coefficients, right? So here we might have the basis functions and then the projections for each of those, and then we sum all those up, recognizing that they're all orthogonal to each other, and that gives us that vector. All right, so let's do an analogous procedure with signals. All right, so now here we've got this same type of thing, except we are maybe for now dealing in the continuous domain. And so we need to use an integral instead of a summation, but we do that from minus infinity to positive infinity. So this x1 of t could be some coefficient times a, let's say a cosine omega t plus phi, right? And then this x2 might be another signal, and we're looking at this inner product between those two signals. Right? So could we come up with a basis function for this x2 and do the same type of thing, where once we've kind of vectorized a something, then we only really need to keep track of the coefficients, right? Because these unit vectors are implied. They're in the back of our head. We always know that if we're dealing with an XYZ Cartesian coordinate space, then we've got unit vectors of 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? So, so can we come up with something like that? Well, to kind of define this as orthonormal basis functions, right? Then the inner product for all of these, when these are different, right? These would be our candidate basis functions, orthonormal basis functions. For them to be orthogonal, when m is not equal to n, then this inner product should produce 0. When m is equal to n, right, when it's phi n times phi n complex conjugate, then that should give us a 1 because it's normal, right? It's so the ortho part means that there's no kind of overlap between each of these. There's no projection from one to another. They're perfectly orthonormal or orthogonal, and they're normalized, right? So now let's assume that this S of t here is a deterministic signal with finite energy, right? So it's not random, and yeah, it's not like cosine would have infinite energy, right? So we're going to make sure that that rolls off here, right? So now we can then take this S of t, and we can take some set of basis functions. We haven't said what those are yet, other than that they obey this property up here, right? And then we can create these coefficients for each of these and sum them all up, and that will give us an approximation for this S of t, right? So now, does this look familiar to you? Right? Think about this for a moment, and does this concept here, or this equation in particular, look familiar to you? Well, you studied this extensively last year. and we'll get to that. I know I'm going to kind of go fast. If I was in class and lecture, I'd make you all raise hands and answer that. But keep thinking about that, right? So now, given a set of finite energy signal waveforms, right, we can construct, so that's an assumption that we're dealing with, right? We can construct a set of orthonormal waveforms using this Gram-Schmidt orthogonalization procedure. Now, the book actually has an appendix on this, so if you're interested, you can look that up. We're going to kind of skip over this for the sake of time, but if you ever need to do that, there is a kind of a fundamental or methodical procedure on how to create a set of orthonormal waveforms, so you can generate them. We use these orthonormal waveforms as a basis set and express our signal as this, right? So this is the same equation, maybe slightly different form, but it's doing the same thing here, right? So where now we have these this signals, set of signals here that are represented as these coefficients times these basis functions. Each signal now can be represented as a vector, right? So here, this SMM here is just saying that we might have multiple different signals that we're dealing with, right? M different signals, each of which is represented by n terms of this and coefficients times these basis functions. So if once we derive these basis functions, we kind of know they exist and we assume that they exist and they take a particular form, and we can kind of drop them from our notation. They're still there in the background, right? So this is still ultimately your approximation to your signal, but we can kind of ignore these in our nomenclature and just keep track of these coefficients. So that's pretty handy, right? So what this does is this gives us this ability to visualize our signals using what we call constellation diagrams here, right? So here, yeah, maybe this is x-axis, this is a y-axis. We're electrical engineers, so let's think of this as a real axis and this as the imaginary axis. And we can represent 4 different signals with a coefficient here with some of these basis functions here, right? So, and this might be a 1, 1, or maybe it's a square root of 2, square root of 2, right? Depending upon what our total energy is that we want to represent in this diagram, right? So this would be, let's see, a -1, 1. This would be -1, -1, and a 1, -1. Right, so we've got these. This is a signal, right? This is representing a signal in the time domain, right? And so is this, but they are distinct, right? And we can we don't have to worry about the e to the j omega t plus phi or the a cosine omega t plus phi. We don't need to worry about that. We're just going to worry about where it is assuming these basis functions. All right, so let's go back. Now maybe you've been thinking about this a little bit. So this looks a lot like a Fourier series expansion, right? So this could be the e to the j omega n t type of thing, right? And you would have a whole bunch of different basis functions, right? So Here, these don't have to be that complex. We can represent this very easily on the real or the complex plane, right? So sometimes we'll use the real if it's not two-dimensional, or we'll use this complex space, right? So the key is here, the takeaway, again, we're not going to be deriving these basis functions or whatever. I think you'll see that you're going to get used to just dealing with this type of constellation space. All right, but before we dive in there, let's talk about two different kinds of modulation. One that's memoryless, and then one that's memory, which we'll talk about in a moment. So bits represent information, right? They're logical. We label them 0 or 1, right? That doesn't carry any significance in terms of the voltages or anything else associated with the signal, right? And we denote that as a capital I. Symbols are physical entities that it is adapted to the channel, right? So if you're putting this on a wire or a PC board trace or something, then you might have a symbol that lasts for some period t. Let's say it's equal to 100 microseconds in length, right? And it's maybe we map a 0 to a -1 volt and a 1 to a +1 volt. And then so now that symbol is a type of let's see if I can come on, let's see. Well, so it might be that, or it might be this, right? And then we could send another one right away, or we might have a little gap between them, whatever, right? So the point is that that's a physical entity that's been adapted to the channel. Now, in RF situations, we need to kind of match frequency and bandwidth to the available channel, right? So now maybe we're taking a bit and modulating up to 100 megahertz, and then we're structuring or filtering its bandwidth to be maybe 1 megahertz wide or something like that, right? So the modulator maps some number of bits to each symbol. And what I've just been talking about would be a K of 1, where we map a 1 bit to one symbol. But we don't have to. We can take a group of K bits, right, coming in, and we can adapt that to some number of symbols, right? So now maybe one symbol is like that, and another one is like that, twice the amplitude, and we might have a -1, and then also one with twice the amplitude, right? So now we might draw this constellation here as something like this, right? So where each one of these dots, horribly drawn dots, represent a different symbol, right? So we can now take and maybe map a pair of bits. I'll just do this kind of arbitrarily here. There's a more methodical way of doing this, which we'll eventually cover. So if I have a bit stream I coming in, then I group them in terms of K's. Here, K would be equal to 2, right? So I'm going to take 2 of these bits coming in, and I'm going to map them to these symbols using this modulator. And now, if I see a positive, let's say 1 volt, and this is 2 volts, these would be negatives, right? If at the receiver I see a positive 1 volt, then I know that that corresponds to bits 0, 1, right? So now if I have bits, a grouping of bits 0, 0, then I send out a -1. The point here is that we only have to send 1 symbol for every 2 bits coming in, instead of kind of the simplest version where K is equal to 1. I have to send a symbol for every single bit. So so our symbols are coming out half the rate that these bits are coming in. All right, so so the symbol K, the symbol is chosen from a set of M symbols based upon the K input bits. Each set of K bits is mapped independently of any other set, right? So this set is mapped independently of this one and this one, right? So we're only looking at those. And okay, so there are M equals 2 to the K symbols in the set. So this is a good exam question, by the way, to say, okay, if K is equal to 3, how many symbols do I need in my symbol set, in my set of symbols, to encode those, right? So K is equal to 3, 2 to the third is 8. So we would need 8 different symbols. Now, for any given 3 bits that come in, we send out 1 symbol, right? But we choose that 1 symbol out of a set of 8, right? And there's this mapping of these 3 bits to a particular symbol, right? So there's a unique 1 to well, 3 to 1 type of mapping, right? So so little m, right, whatever symbol we send out now, is somewhere between 1 and 2 to the K, in that case 8, right? So it might be 1, might be 8, might be 6. So these M are representing the individual symbols, right? Okay, so if K is equal to 4, then we need 16 different symbols. Again, we're only sending out 1 symbol at a time, but we need a set of 16 to draw from. So that's memory list modulation. We're going to spend a lot of time on this, right? We're going to look at different ways of creating symbols to deal with these grouping of Ks coming in, right? So let's look at what happens if we include some memory into this. So now our mapping is a function of the current K bits, but also the past some number of bits, right? L might be 2, so we might look at the previous 1 bit, or L might be 7, something like that, right? So we're looking at some number of bits. And L is called your constraint length, just terminology there. And we often implement this. We can implement this with a finite state machine. Remember, you studied finite state machines and your digital logic course, right? Moore and Mealy type of state machines, right? So now we need 2 to the L minus 1 times K different states in that state machine, right? So we've got, some number of K bits that we're dealing with, current bits, but then we also have this kind of history of bits that we're trying to deal with too. And so we represent those as 2 to the L minus 1 times K states. Each time instant, we're going to move from time that's a lowercase l minus 1 to lowercase l, according to the input, the current state, and the state transition function. And then we're going to output m sub lowercase l, right? A particular symbol, right? One of m different symbols at instant l, according to the output function, right? So remember back to those state machines, right? So now we have here, this is our output function, right? What are we going to output? M sub l, and that's going to be some function of the current state and the current or new inputs, right? And then that also, we're going to have a new state, according to a state transition function, right? So that's our output function, f sub m. F sub s is our state transition function. So we're going to transition from the previous state to the new state based upon what state we're in and the input bits, right? So, all right, we'll look at how we doing on time here. Okay, good. So now let's look at rates and energy. We're covering a lot of material here, and don't worry, we'll keep reinforcing some of this material as we go from lecture to lecture. So rates and energy. A reasonable design objective is to maximize the rate of information transfer while minimizing the energy required to do so, right? That's kind of the job as an engineer, as a communication engineer, right? As some design objective. There might be other objectives associated with it, other constraints, but ultimately we want to maximize the rate of information transfer while minimizing the energy required. So I want you to continue to be mindful of the difference between symbols that are these things that are adapted to a particular channel, wired, wireless, maybe optical, could be sound even, right? But bits are logical things, right? They don't really exist in the physical world, not even inside a microprocessor. That's still, some number of millivolts, right? So they're logical things. And we're going to send a symbol every period t sub s, right? So T's, cap T standing for a period, and S is for the symbol rate, right? So the symbol period, we take the reciprocal of that, that gives us the rate, right? So we might say R sub S, actually give that. So we might say R sub S there is equal to the reciprocal of the period, right? So the period would give us units of second, or to be complete, seconds per symbol. Rate would give us symbols per second. Since K bits produce one symbol, right? Let's go back to here, right? K bits produce one symbol. Okay? Then our bit period is equal to the period of each bit is equal to the period of the symbol divided by how many bits are grouped to make that symbol, right? So if it's a 1-to-1, K is equal to 1, then they're the same, right? If we, in our first example, we mapped 2 bits to a symbol, then our bit period would be half of the symbol period, right? Or I also did an example where k is equal to 3, right? And then we would divide our symbol period by 3 to give us our bit period, right? And then the kind of the opposite relationship with in terms of rates here. So since we're dealing with fundamentally moving bits of information, right? So sometimes we'll just use R, but more complete, that would be R sub B for the bit rate. And that would be K times the symbol rate. So if our symbol rate is 1 megahertz and K is equal to 2, then our bit rate would be 2 megabits per second, right? We can also put this in terms of M, right? So you remember M is equal to 2 to the K. So if we want to represent that, we take the reciprocal of that operation, that would be log base 2 of M, right? So M might be 8, log base 2 of 8 is 3, log base 2 of 4 is 2, and log base 2 of 1 is 1, and so on, right? So in modern communication systems, you might see M easily 1024, so give you a K of 10. Could be 4096. We're really pushing it then. That would be a K of 12 then, right? Yeah, 2048, 4096. So but more typically, M might be 4, 16, or 64, typically. So, all right. Now, if we have a certain period and a certain rate associated with bits and symbols, right, then we could also look at the relationship of energy, the bit energy. So here we can say that we can start to introduce our probabilities back into things, right? And look at what's the probability of some symbol being or signal being sent, right? And we can break that up into the M different ones and look at the different energies associated with those, and then scale those by the probability. Maybe it's all equal probable. If you have M is equal to 4, then P sub M might be 0.25, 0.25, 0.25, 0.25, right? For all of those. They might be equal probable, but not necessarily, right? And we need to be able to handle mathematically the case where they're not, right? So, and then this will give us the average energy of the set of symbols, right? So if we think about, let's see, did I erase that, or do I still? Yeah, I think so if we remember that in one case, let's see, let's try to get that back here, that I had M equals 4, right? And we arrayed those on the real axis, then we would see that these guys have a smaller energy than these guys do, right? So, or I could array them as that other diagram I showed you earlier. Oops, ignore that. And now each of these, actually, they're kind of the same distance from the origin here, right? Which is how we might describe their energy. So these would have the same energy. These would have different energies, right? So E sub m might not be a constant, right? So, so another way of now relating that to the energy per bit, right? So again, bits are logical entities, but not physical, so they don't really have energy, but it's useful in our analysis and our comparison of different systems to allocate this energy in the symbol to the energy in the bits, right? And we do that saying that, well, there's k bits per symbol. So let's take the energy, that kind of average energy in the symbol, and divide by k, and we'll allocate that to the bits, right? So another way of doing it, of course, is k is equal to log base 2 of m, or m is equal to 2 to the k, right? So those are reciprocal operations. So we're just subbing in for k there. So sometimes we want to work with m, sometimes we want to work with k. All right, so these relations simplify with equal probable symbols and or identical energies across the symbol alphabet, right? So we talked about here, these would be equal energies, these would be non-equal energies. In a particular situation, maybe this bit is much more likely to be sent, or this symbol, I'm sorry, the symbol is much more likely to be sent than this one or this one. Don't know, right? So just understand this is the more general case, but oftentimes they're equal probable, and sometimes there are equal energies, not always. Right? So, all right, whew, that's I know that's a lot. We still got I think 15 minutes, so let's look at some examples of this. So we'll look at pulse amplitude modulation, and we're going to look at a memoryless version of this, right? So let's create a symbol alphabet using different amplitudes for the signal, right? So it's a pulse amplitude modulation. So we studied amplitude modulation in analog version. Now we're looking at it in a more, well, ultimately discrete. We haven't really discretized these things yet, but that's coming, right? So now here we take some pulse that we're going to send, right? And that could be a cosine omega t at a particular frequency, omega, right? And but it's going to last for a certain period of time, right? Because we ultimately are going to discretize this in the time domain also, right? And then so now we can map our symbols, our m different symbols, right? So we've got cap m here and a particular m. We can modify this pulse with some amplitude, and that will give us the symbol S sub m, right? And so P of t is a pulse of duration cap t, right? Or we could put T sub s in there, most likely. Its shape is an important design factor, and we'll look at that in the future, right? And but you can just assume that it's like a pulse of a cosine for now, right? A rectangular pulse of a cosine signal, right? So so A sub m here, we're going to say we're going to encode as 2 times m minus 1 minus cap m. Okay, and what does this do? This helps us balance the spacing about 0, right? You can plug in some values there. You can plug in 1 So let's say m is 4, right? So 2 to the 4th would be 16. So we'll map in 16 different bits per symbol. So we need, I'm sorry, I said that wrong. We'll map in 4 bits to a symbol. So we need 16 different symbols. Am I saying that right? Let me make sure. Yeah. So m is equal to 16. And so let's plug in 1 here for m. So we'd have 2 minus 1. So that's 1 minus 16. So that's going to give us a minus 15, right? Or we might have 14 here, right? So it'd be 28 minus 1, 27 minus 16 would be 11. Am I doing the math right there? So in some cases it's going to be negative, some cases it's going to be positive. This is going to balance out, right? So maybe I should have stuck with my m is equal to 1 would have been, or k is equal to 2 would have been a little bit easier to see, right? But all right, so let's look at the energy in the symbol now. And so we do that by taking our amplitude and squaring it, and then integrating from minus infinity to plus infinity. Well, we said that this pulse has a period of t, so elsewhere it's going to be 0, right? So, so this should be finite, right? But we can kind of replace this part of the equation, this p squared t, with this energy of the pulse, right? So because this is going to stay the same, right? This is what we're changing. This is always going to be the same. And so we can treat it really, integrate it in that, and that'll be a constant, right? And then this is a coefficient. It's even though it changes from symbol to symbol, it's not a function of t. So we can treat that as a constant and bring it outside that integral. So this e to the p is that energy in p of t. So we just integrate that, and oops. So now we can look at, again, the average energy of a symbol, right? So now we can look at all these and sum up these. Here we're making the assumption that they're all equal probable, right? Because there's no row out here representing, or p. That would be confusing because there's no probability coefficient out here multiplying these, right? So we're assuming that they're equal probable. So we can then pull out this EP, because that's always the same, and then we just divide by the m. In the earlier form where we had the probability out here, that was kind of accounting for this m, right? So you would have some probability where they would all sum to 1, but here we don't have that probability term here, so it's essentially like probably a 1. So we have to then divide by m to get the right average, right? So you just think about that a little bit. I think hopefully that's clear. So we can sub in this equation, right? And we'll get something like this, right? Where we factored this 2 out, and now we just kind of substituted in, however big m is, these values, right? So that's just working that previous equation. And we can, if you've studied math in terms of series, finite series here, you can represent this with this form, this equation right here, and we won't derive that. Just trust me. And so then we can simplify these m's cancel, that 2/6 becomes 1/3, and we end up with this relationship right here, right? So we can put that in terms of our m also, right here, where this we're now moving from the average energy per symbol to the average energy per bit. So now we basically are dividing by k bits per symbol, or that's also equal to log base 2 of m, right? So again, m might be 8, log base 2 of 8 is 3, right? So 3 bits per symbol. All right, so this is how we would allocate energy for pulse amplitude modulation where they're equal probable pulses. And so now we did that low pass equivalent circuit, right? Low pass equivalent representation of our RF signal. So let's dig that out again. And here we remember we kind of had that analytical signal, this low pass equivalent of the symbol. And then we have this e to the j 2 pi fct, right? And this is that carrier signal. But then to extract out the actual one, the SMT, then we're going to take the real part of that, right? So we take that low pass equivalent representation signal, we multiply by this carrier, and then we take the real part of it, and that gives us the real signal again, right? So that would be this A sub m times this g of t times cosine 2 pi fct, where g of t now is going to be kind of our pulse, right, that we're dealing with, right? And so that's just kind of this gating function for this period, right, for the symbol. And then A sub m is now modifying the amplitude of this, right? So here, this might be a +1. Maybe this is a +2. Note that this one has a different phase of this one, right? So you see that here. We're heading down, you know, this sine wave is starting to cycle, but then it reverses course. Well, that's the same as multiplying it by -1, right? Or shifting it by 180 degrees. So this is essentially the negation of this one, right? And let's see, I think this one is a negation of this one, right? So if we designate this as a +1, that might be a +2, that might be a -2, and this might be a -1, right? So, all right, so our P of t here, right, from our previous equation, is this G, or this gating type of representation, times this carrier, right? And so again, using this low pass equivalent circuit, we can kind of, while we're working with the data, we can kind of ignore all of this high frequency stuff and just focus on these transitions here. All right, so let's look at some examples here. This would be m equals 2, or k is equal to 1. So 1 bit gets mapped to 1 symbol. If it's a 1, maybe it gets mapped up here to +1 volt or +10 volts or something, right? And if it's 0, it gets mapped down here, and maybe this is -1 or -10 volts, right? So these are our constellation points, right? So these are our vector representation of this whole mess, right? So why did we do all that vectorization earlier in the lecture? So we can just draw this diagram and you know what is going on, right? So let's look at m equals 4. Now we have 4 different symbols. Each maps 2 bits into a symbol, right? So as our bits are coming in, if we get a 0, 0, we emit this symbol. If we get a 1, 1, we emit that symbol, right? So m is equal to 8. Now we've got 8 different symbols. And if we take log base 2 of 8, we get 3. So we have 3 bits mapping to one of these symbols, right? There's a one-to-one mapping for this sequence of k bits to a particular symbol. So are these equal energy symbols? Think about that, right? Look at that. Are those equal energies? How does the energy change with M, right? What if we have a peak power limit on our transmitter? So we have a transmitter that can transmit 5 watts and no more, right? Maybe that's limited by our hardware, maybe it's limited by the FCC or something, right? So what is special about the mapping of the bits in these symbols, right? So we'll I think we're going to run out of time, so maybe I'll stop there and we'll just talk about these. So are these equal energy symbols? No, right? So this symbol has a lot more energy than this one does, right? So these, okay, these are equal energy, right? So because we square the amplitudes, so this is +5 and that's -5. Well, they both have an energy of 25, right? And but now these are different energies. These are very different energies, right? And if we have a max limit, then let's say the most we can do is 5 watts, then we've got to keep all these maximum cases at 5 watts, right? And an amplitude that would correspond when you square it and deal with things, then that gives you a maximum of 5 watts. Well, if we're constraining these outers, then really what we're doing is we need to squeeze all these together, right? And here we've written it such that there's essentially equal spacing between these guys, right? Notice that this space is about the same as that space, is about the same as that space, right? So we might have some noise, right? And so instead of being right there when we receive it, it might be all over the place here, right? And if we send this one, but there's so much noise that it kind of by the time we receive it, it's over here, then our receiver doesn't know any better, and it's going to say, well, that's closest to this symbol, so I'm going to assume that that corresponds to a 0, 1, when it was really a 1, 1, right? Or if we're, got so much kind of positive noise voltage at a particular instant, then we might confuse it for this symbol, right? If we're constrained on these outer points, then the more M we have, the closer all these things have to squeeze together, right? So this is the same power as that, as the same power of that. That means that as we have more of these intervals, that those intervals have to get smaller and smaller. That means that it takes less noise. Here, it takes a lot of noise from here to get confused. This would take half the level of noise, right? If you can just imagine these things being squeezed together. And even worse in this case, right? So if these points were all the same amplitude, right, representing the same power, then these all have to squeeze together. So the more of these things, the worse it gets, right? So now let's see. Let's do one last little thing. I know it's late, so let's draw in this Shannon capacity theorem, right? And because this might show up on your test, right? So hang with me. This won't take long, right? So 1 plus signal divided by noise, right? So now if our signal is can be strong enough, right, then we can relative to the noise, then we can go to a higher M, and now we can send 3 bits in the same period of time that it takes to send 1 bit, because the bandwidth here is going to be driven by your symbol rate, right? How many symbols are you sending per second? But if we can send multiple bits per symbol, because we've got lots of signal power to deal with relative to the noise we might have, right? Then we have more signal, then we can go to a higher M and encode more bits per symbol for the same bandwidth and get a larger capacity, a larger rate, data rate. All right, so have a good weekend. If you're confused, not weekend, I don't mean weekend. If you have a good few days, and if you're a little uncertain on things, please schedule an appointment with me over the next couple of days. All right, I'll update the exam preview as necessary, and as I develop the test, I'll make sure that there's no blindsiding going on.